Okay, let's talk about Planck's oscillators, or quantized energy, or quantized oscillators. An oscillator, so it's Einstein who came along later and said that energy comes in quantized amounts of NHF, but as far as Planck goes, it's an oscillator, oscillates at a certain frequency f, but its total energy must be a integer multiple of h times f, where h is Planck's constant. What do we mean by that? What that means is that in a quantized oscillator, the change in energy, the smallest change in energy is hf, or the amount of energy that the quantized oscillator can change in is an integer multiple of f, right? So hf is the minimum. I guess actually I should be more careful on that the change in energy can only come in chunks of NHF, right? That's what it means to say that the energy is some integer multiple of NHF, that you can only change it by some chunk, by HF or any multiple of HF. I don't know why I'm having so much trouble saying this. Okay, so let's just take, for example, a macroscopic mass on a spring. Now, Planck did this for microscopic atoms in a cavity, and the atoms modeled as masses on springs. But this is true for macroscopic masses on springs. And what does that mean, that it's true for macroscopic masses on springs? And macroscopic just means things you can hold in your hand, a mass on a spring in a classroom. What does it mean that it holds for that? It means that even a mass on a spring that you have in the classroom can only change by certain amounts of energy. Say, no, I mean, that's ridiculous, right? I mean, they're continuous, right? You can pull that mass out to any amplitude, and we know that the energy of a mass on a spring is 1/2 Ka squared. Don't forget that the mass on the spring, right, we have a mass m, spring k, the total mechanical energy is 1/2 mv squared plus 1/2 plus 1/2 kx squared, and when x is a maximum, v is a minimum, and that's why it's equal to 1/2 k a squared, because it's 1/2 m times 0 squared plus 1/2 k times a squared, right? So the total energy in a mass on a spring is 1/2 k a squared, and say, well, a can be anything. If a can be anything, then how can this hold? How can we have that we can only change it by NHF? And the fact is that macroscopically a can really be anything to our ability to measure it. That a change of NHF or a change of HF, a single quanta of energy, is so small it's immeasurable. But it is true that oscillators are quantized and can only come in chunks of HF. But HF is so small that it's not measurable on a macroscopic scale. So let's just see that. So let's just think about our mass on a spring, M and K, and the things that we know about it. We know that the period for a mass on a spring is 2 pi square root of m over k, and so therefore, that's m over k, therefore the frequency is 1 over the period, which is 1 over 2 pi square root of k over m. And let's just say that let's just take a classroom mass and spring and say we've got a spring with spring constant 10 newtons per meter, and a mass of 50 grams, 0.05 kilograms, and go ahead and plug that in to F equals 1 over 2 pi squared to K over M. Do that on your calculator, and you find that it's got a frequency of 2.25 hertz. So this mass on a spring will oscillate with a frequency of 2.25 hertz. Let's take that mass on a spring and let's pull it away from equilibrium. A distance A equals 2 centimeters, or 0.02 meters, and say, okay, so what's the total energy of this mass on a spring? The total energy, the total mechanical energy is 1/2 mv squared plus 1/2 kx squared, or also it's 1/2 ka squared. So the total mechanical energy is, go ahead and plug that into your calculator. We find the total mechanical energy is 2 × 10⁻³ joules. And let's find a quanta of energy for this oscillator. A quanta of energy for for this oscillator, right? A single quanta of energy, delta E, the smallest amount that it can change by, is HF, and H is, so a quanta of energy for this, a single quanta of energy, HF, for this oscillator is H, 6.63, is that what, I think that's Planck's constant, 6.63 times 10 to the minus 34 joules times seconds, times the frequency of the oscillator, 2.25 hertz. So that ends up equaling 1.5 times 10 to the minus 33 joules. So now let's just compare these two numbers, right? If the total energy of the mass in the spring is 2 times 10 to the minus 3 joules, and the smallest that it can change by is 10 to the minus 33 joules, 10 to the 30th smaller, that's so much smaller, that's infinitesimally small. You couldn't tell the difference, right? I mean, so yeah, when you're changing the amplitude of that mass on a spring, that it is actually quantized. You can only change it by certain amounts. I mean, at least ideally, but the certain amounts are so small we could never measure it, right? So it seems continuous. So this is the thing about quantum mechanics, is quantum mechanics is typically only observable for small things, right? When we get down to single quanta, when we get down to single atoms and their behavior at low energy. But when you get up to high energy and many atoms, for large numbers, quantization tends to blend together to look continuous, right? It's this concept that 10 to the minus 33 out of 10 to the minus 3 is so small that it might as well just be continuous. Let me just take this mathematics one step further and just make sure we understand that that this quantizes the amplitudes that were allowed, but the quantization of the amplitude is so small in the difference between amplitudes that it would be immeasurable. So let's go one step further and look at this equation and ask, how does the energy change with amplitude? So this is the energy for a mass on a spring. How does the energy change with amplitude? This is calculus. We are calculus gods as physicists. So we want to ask, how does the energy change with, how does E change with A? And that is taking the derivative, dE dA. dE dA, that's a measure of how E changes with A. So if it's 1/2 Ka squared, so it's 2 times 1/2 Ka to the 1. Right? So that's how E changes with A. So therefore, dA, we can solve for dA. dA is equal to dE over Ka. And if dE is the smallest possible change, that's HF over Ka, and F is whatever F is. So we can just plug in the numbers that we had already calculated or were given, and you can find that the smallest possible change in amplitude is 7.4 times 10 to the minus 33 meters. The smallest possible change in amplitude is 7.4. So it's not continuous, the amplitude is not continuous, but the smallest possible change might as well be continuous because it's 10 to the minus 33 meters. The size of a nucleus is about 10 to the minus 15 meters, and we're only good at measuring distances up to maybe a fraction of a nucleus, but not 10 to the minus 33 meters. So this might as well be continuous. But for all that being said, this fixes blackbody radiation, right? It's this quantization that fixes blackbody radiation. Now the theory works, Planck's law works, and we understand that there's a new physics, or Einstein's starting to understand there's a new physics that's coming down the road. Before we move on from this topic, let me define one more thing, something called the quantum number. Quantum number is really, it's just simply the integer that represents a certain measurement. So the quantum number, in this case, it would be n, right? The quantum number in this case is n. There are different kinds of quantum numbers, but it's n, where E equals NHF. So we can ask, what is the quantum number of the oscillator? All that means is, what is the multiplier of HF that gives us the energy of the oscillator? So quantum numbers, typically quantum mechanics is noticeable when the quantum number is small, but when the quantum number is large, we're in the realm of classical mechanics where quantum looks classical. It looks continuous. We can't see the discreteness. Does this make sense? Small quantum numbers usually means we can observe quantum effects. Large quantum numbers usually means that we're in a realm where the quantum mechanics or the quantization looks classical. It looks continuous because things are so close together and there's so many of them. So let's go ahead and just calculate the quantum number of this particular oscillator. So this is the quantum number, right? It's just setting the total energy equal to NHF and also equal to what it is equal to, 1/2 Ka squared, and solving for n. That's the quantum number. Just to get it's sort of a terminology thing, right? HF is an energy, 1.49 10 to the minus 33 joules, but it's the energy per quanta, per single quantum lump of energy. We call that a quanta. So you can think of that as 1.49. You can think of HF as 1.49 10 to the minus 33 joules per quanta of energy. That's quanta of energy. So anyway, we can go ahead, and so that what this is going to give us is n equals some number of quantas of energy, or numbers of quanta. So we can just go ahead and plug in. So we get n, the quantum number, is 1.33, or 1.3 times 10 to the 30th. Or there are 1.3 times 10 to the 30th quantas of energy. Quantum packets of energy in this oscillator. That's a lot of energy, a lot of quanta. That's a large quantum number. Taking this even one step further, I know we're trying to finish up this topic, we can talk about energy level diagrams, which you have probably seen somewhere before. If you've taken some chemistry at least before, we can talk about energy level diagrams, and we could usually talk about them from the point of view of a single atom or something like that. But the concept of an energy level diagram is indeed that the energy is quantized. If you haven't seen them before, they might look something like this. Or more likely what happens is the energy levels get closer together as we go up. So these are energy levels, and the energy increases in that direction. And typically you talk about the ground state energy of an atom or a system, and that would be the lowest possible energy it can have, n equals 1. And then as you go up, the quantum numbers of the energy levels go up, n equals 3, n equals 4, n equals, again, so this is just a different system, n equals 2, and we'll see this more later, ... The quantum numbers of the energy levels go up, and the energy of the energy levels go up. So for the simple harmonic oscillator, this would be HF, this would be 2HF, this would be 3HF, etc., where the energy of the energy level is NHF, right? And what you often see, what you normally see for the quantized oscillator, they're evenly spaced energy levels. For a real atom or molecule, what happens is the energy levels get closer and closer together as you go up, which is one of the reasons why they start to look continuous, because those energy levels get so close together. Because the energy levels go not proportional to n, but go as 1 over n for a typical atom. They go as 1 over n, so they get closer and closer together as you go up. But anyway, this is what an energy level diagram looks like. You might talk about an atom in its lowest state is in its lowest energy level. If you excite it, you might excite it to a higher energy level. Atoms will move up and down between energy levels. Okay, that's all we need to say about energy level diagrams right now.